Hello everyone. Today's topic of my presentation is Chapter 2 of MMIC. This book is written by Professor Kim Nam-myo. In this chapter, the basic processing sequence used to fabricate BJT integrated circuits is reviewed. Additionally, it's important to know how to use the foundry company. The first section discusses the foundry service, and the second and third sections present an active device and passive device, respectively. Finally, in the fourth section, the layout design rule is described. This will provide a background for the layout and physical design of the chip. The contents of this chapter are from Kimco, which is a modern foundry company. Throughout this text, we will rely on the technical specialists from Kimco Company. Both MMIC layout and MMIC fabrication are multi-step processes. Because layout and fabrication are so interdependent, they are considered here as part of one overall process. The curriculum illustrates the overall MMIC layout and fabrication process, featuring a block diagram of the foundry service process. The HBT process can be separated into two parts for explanation. One part is concerned with the transistor aspect. The other part includes the rest of the MMIC and its backside. On top of the basic buffer, the 6-inch in-gap HBT processes are shown in Figure 2.2. Three types of processes are detailed in Table 2.1. Depending on the specification of a particular circuit, the specific process will be chosen. This part is active devices. The active device must have the characteristics of amplification and nonlinearity. Additionally, it requires a DC bias, such as a TR and a dioide. In this section, only HBTX are mentioned. The 325 HBTX have a heterostructure that takes advantage of its superior transport properties, including high electronic mobility and velocity. The 325 HBTS are based on the substrate of a gas material with high resistivity. Figure 2.7 presents a cross-sectional view of the in-gap gas HBT because of the heterostructure junction, which possesses a bandgap difference between the emitter and base. This system has a higher emitter junction efficiency and a higher current gain than the HAMO junction. To increase electron mobility, a very high base doping concentration and a very thin base thickness are achieved by expansional growth. This part is in-gap gas HBT devices. First part is Introduction to High Linearity Process Active Device. Its name from the intrinsic linearity of the in-gap heterojunction bipolar transistor, characterized by uniform current gain characteristics. Then is characteristics of HLF 2 multiply 2 multiply 20 device. Electrical characteristics of the HLF device include beta of 150, Ft of 50 GHz, and FMX of 80 GHz, highlighting its high performance. The design incorporates in-gap gas HBT, necessitating consideration of the self-heating effect due to gas lower thermal conductivity compared to silicon. Utilization of VBIC module for in-gap gas HBT. The MMIC model, accounting for self-heating effects, is employed for in-gap gas HBT due to its sensitivity to junction temperature, impeding current gain, and base emitter voltage. Thermal resistance plays a crucial role in determining junction temperature and device lifetime. With Konghu, in-gap gas HBT processes offering low Rs for enhanced lifetime. Next is the introduction of 325 HBT MMIC structure. The 325 HBT MMIC structure was conceptualized by William Shockley in 1948, with detailed theoretical analysis provided by Kromer in 1957, featuring 17 process levels, 2 metal layers, and a substrate attaching for emitter, base, and collector establishment. The HBT structure is illustrated. Next is in-gap latch and noise reduction. In-gap latch, depicted in Figure 2.10, survives to prevent surface recombination currents, significantly reducing 1 divided by frequency noise and enhancing oscillator design by minimizing phase noise. The emitter to base spacing influences 1 divided by frequency noise reduction, with the in-gap latch mitigating surface recombination currents, thus extending device lifetime. This part is modeling. The section presents an instruction of parameters necessary for the MMIC module, encompassing parasitic, intrinsic, DC, and AC parameters to achieve a comprehensive model. Parameter extraction and optimization involve DC measurements using a DC source monitor and AC measurements via a vector network analyzer. Modeling software such as integrated circuit characterization and analysis program and advanced design system packages aid in data analysis, simulation, and optimization. The IC-CAP offers features for instrument control, data acquisition, graphical analysis, simulation, optimization, and statistical analysis. It can be integrated with external simulators like ADS for enhancing modeling capabilities. The modeling measurement setup provides an insight into an experimental configuration for parameter extraction. This part is passive devices. It's the extensive use of passive devices that makes MMIC design so different in comparison to the conventional integrated circuit design and layout. In MMIC design, passive devices are used for impedance matching, DC biasing, phase shifting, filtering, and many other functions. This section describes the key passive devices that are used in MMIC design. In this section, a wide range of distributed transmission lines, MIM capacitors, speaker inductors, resistors via hoods, and paths are shown. First is the transmission line. The microstrip is a flat strip of conductive material separated from a single ground plane by a dielectric material substrate, such as GAS. In Figure 2.3.1, the physical parameters of the line metal are shown. The microstrip line lacks the sheltering advantage of the strip line due to the absence of a second ground plane, resulting in higher radiation loss. It also has some advantages such as micro strip line offers the stability for trimming within a circuit, providing flexibility during design and optimization process. Next is the dielectric constant replacement. In microstrip lines, the dielectric constant must be substituted with an effective dielectric constant since part of the electric field resides in the dielectric material and part in the area. Next is the design considerations. Design curves are available to aid in selecting microstrip dimensions to achieve specific characteristic impedance or other required parameters, enhancing design accuracy and efficiency. Last is the utilization in microwave circuits. Microstrip lines serve as valuable interconnection components in microwave circuits, facilitating the seamless integration and functionality of various circuit elements. Next is the MIM capacitor. First is the introduction of MIM capacitors. MIM capacitors have become the most popular type due to their high capacitance per unit area, enabling smaller and cost-effective circuits. MIM capacitors consist of two metal plates separated by a dielectric layer. The dielectric layer overlaps the first metal layer, while the second metal layer typically has a smaller area. The capacitance value is determined by the area of the air bridge post. The benefits of MMIM capacitors is MIM capacitors help minimize fringing fields to ground and shorts between the metal layers, enhancing circuit performance. The inclusion of air bridges further reduces parasitic capacitance. The challenges and considerations is due to the thin dielectric layer, MIM capacitors are susceptible to fringing effects, and even a single failure can compromise the entire capacitor and chip. The dielectric layer thickness is fixed in open foundry services, and the capacitance is approximately linearly proportional to the air bridge via metal. This part is the spiral inductor. The spiral inductor have gained popularity due to their high Q factor, making them a preferred choice for various applications. Keiku provides spiral inductors with inductance values ranging from 0.28 to 24 Nh. They offer two types of square spiral inductors, each with unique structure features. The first type, shown in figure 2.34, features an entire air bridge and air bridge post. The second type, known as the microstrip line type, utilizes the outward shape of the first type and incorporates an air bridge in one portion. This part is the resistor. Resistors in MMIC can utilize a doped semiconductor layer or a deposit thin film resistive layer. The material commonly used for thin film resistors in MMIC is nickel. The advantage of sputtered thin film resistors is sputtered thin film resistors offer improved linearity and lower temperature coefficients compared to other resistor types. These resistors can achieve sheet resistance of 50 ohm per square, which is convenient for circuit designs in achieving desired resistance values. Detailed layout rules for nickel resistors are provided in the section on layout design rules, offering guidance on their implementation and integration with MMIC designs. This part is the VI hole and pad. Backside VI holes serve the purpose of connecting devices or RF circuits on the front side of the substrate to the metallized back-end side for grounding and thermal dissipation. The substrate via holes are designed to accommodate 95 8 plus or minus 10% thickness of JS wafers, ensuring compatibility with various substrate thickness. Via holes can be mounted in RF devices as a single port, connecting the front via pad to the back-end side ground, facilitating accurate simulation and analysis. The configuration and physical parameters of via holes, including dimensions and placement, are critical for their functionality and performance in RF circuits. Next is the layout design rule. Relatively few design equations are used in the description of passive devices because they highly process dependent. For a particular MMIC fabrication process, the manufacturer's design manual is the essential authority on the exact design rules for device layout, as well as the appropriate design curves and equations. Nevertheless, in many cases, the design manual survives as little more than a reference guide for process data. Hence, this section provides a significant amount of background information, which is essential for all but the most experienced designer. This part is general considerations. The stepping tile size generally is the first thing that must be considered. In the MPW process, the wafer is shared, which is why the size of the resulting chip is limited. Additionally, the chip shape is a performant square as a result of this process. The maximum width and height of the chip are both restricted to 15 mm. For the same reason as the first consideration, the emitter direction must be a common parameter. This is shown in figure 2.39. On the bottom of the wafer, the groove is hollowed to establish up from down. Additionally, there are alternative ways to denote the downside on wafers. This part is the general considerations. MPW is an abbreviation for the term Multiple Project Wafer. As mentioned previously, users may share the wafer during the manufacturing process. This is because it's too expensive to use the whole wafer, and an individual wafer is frequently too large for one project. Hence, each user shares the wafer. Each customer uses the given rules in designing the desired circuit. After that, the company gathers each circuit and fabricates the chip on one wafer. The term MPW comes out of this process. Additionally, the specification 16 means the customers will share one mask. The width of the scribe line is 100 mm. Figure 2.40 illustrates this description for ease of understanding. When the layout database is submitted, it should be in JDSII file format. JDSII stream files must have default JDSII units. This format uses the standard cell library that key company supplies. These files are also used to unify the entire set of chips on a wafer. Here, acute angle corners are shown in the figure 2.41. 6 types of simple layout design rules are described in Table 2.6. There are 19 layers used in the fabrication process of keyhole. The full names of the layer IDs are shown in Table 2.7, and each layer is described in the right figure. All of the components will consist of these layers. The following section presents each device. Some of these layers are used independent of other requirements, and the others should be designed. The former set is provided by the company, so the layer should only be partially treated by the customer. Establish the resistor and transmission lines, the final persistence. The library itself shouldn't be changed. The following design rules are specifications for the wafer as given by Keiku. First is Nickel NCR. The minimum width of NCR is 2 micrometer. The minimum spacing of NCR to NCR is 5 micrometer. The minimum spacing of NCR to IE is 2 micrometer. The minimum overlapping of NCR and IMS is 2 micrometer. The minimum extension of IMS to NCR perpendicular to the current flow is 0.2 micrometer. No donut pattern allowed due to the lift-off process. The maximum current density of the nickel resistor is 1 mA per micrometer. Based on equation 2.3.1, the desired resistor can be designed. The designer can decide the shape of the resistor depending on the available space in the circuit. The physical parameters of the nickel thin film resistor are given in Table 2.8. The second is IMS. The IMS is a layer that is patterned before sputtering the seed metal for electroplating. The minimum width of the IMS is 1 micrometer. The minimum width of the IMS, the non-active device area, is 1.2 micrometer. Minimum spacing between IMS and MMS is 3 micrometer. Minimum surrounding of FNV by IMS is 0.2 micrometer. The third is IM. The minimum spacing between IM and IM is 2.4 micrometer. The fixed surrounding of the IMS by IM is 0.3 micrometer. The maximum current density of the interconnect metal is 10 mA per micrometer. There is no donut pattern allowed. The fourth is the SNV. The minimum width of the SNV is 3 micrometer. The minimum surrounding of the SNV by IM is 1 micrometer. The fifth is the ABP. The minimum width of the ABP is 4 micrometer. The minimum spacing between ABP and ABP is 5 micrometer. The minimum spacing between ABP and IE is 5 micrometer. The minimum spacing between ABP and IM is 4 micrometer. The minimum surrounding the SMV by ABP is 0.5 micrometer. The sixth is ABM. The minimum width of the ABM is 5 micrometer. The minimum spacing of ABM to ABM is 5 micrometer. The fixed surrounding of the ABP by ABM is 0.5 micrometer. The ABP must be corners of the ABM. The maximum current density of the air bridge metal is 20 MA per micrometer. There is no donut pattern allowed. For the FPL, the minimum width of the FPL is 30 micrometer. The minimum surrounding of the BSS by FPL is 12.5 micrometer. The minimum spacing between FPL and FPL is 30 micrometer. For the PAD, the minimum width of the bond pad is determined by the assemble's capability, and the typical bond pad size is 100 micrometer multiplied 100 micrometer. The minimum width of the test pad is 75 micrometer. The minimum spacing between two bond pads is 25 micrometer. The minimum surrounding between bond pad and FPL is 12.5 micrometer. The minimum spacing between the scribe line edge and the bond pad is 12.5 micrometer. The transmission line is composed of two layers, IMS and IM. For the cautions, fixed surrounding of the IMS by IM is 0.3 micrometer. There is no donut pattern allowed. Fixed surrounding of the ABP by ABM is 0.5 micrometer. ABP must be corners of the ABM. This part is the DRC. DRC stands for Design Rule Check, which is a crucial step for engineers to ensure that their designs comply with manufacturing specifications. There are two types of DRC. First is quick check, the other is custom check. The quick check involves the rapid assessment of minimum width and spacing requirements, typically for basic designs. The custom check involves a thorough examination according to pre-written rules tailored to specific design requirements. The DRC procedure ensures that designs adhere to predefined rules, minimizing errors and ensuring manufacturability. The procedure is started with the definition or selection of a design rule, as the circuit runs according to certain rules, and then the result is loaded. Based on this procedure, the customer is capable of locating any errors. The DRC message window, which provides information regarding the standards of the current design rule check, is shown below. My presentation is over. Thank you, everyone.